should actually start recording. Okay. So when we experimentally determine structure, we'll look at a variety of forms of spectroscopy. Because you all watched the video. That upper left is showing what? That's the type of bond associated with which form of spectroscopy? IR, or infrared. These two, which type of spectroscopy? We're looking at our NMRs, our H NMR, hence the H is circled, and our carbon NMR, hence the C is circled. Okay. The lower left-hand corner, MS for mass spec. You are responsible for being able to analyze IR and NMR to their fullest extent. The mass spec will show up on the exam, but in a much more limited sense. Okay? That's why we have things relatively briefly addressed here. Spectroscopy takes time to learn and practice. Unfortunately, in the sequencing of how we've got the chapter set up, we can't start with it, we have to end with it. Okay? Which means you have less time to practice for the exam in 2 weeks. Okay? That's why I posted the video content on how to solve, which is ultimately what you're going to be responsible for. So what we will reserve class for is a little bit of that practice with spectroscopy and some of the theory behind it. But the actual solving is now completely dictated to the internet, okay, and the lab. It's an actual lab assignment. For those of you not in lab, do it anyway. Okay? I highly encourage you to do it, okay, and work on that spectroscopy practice. For students that have been asking about it, we take a look at, just to give you a rough idea on what's happening here. We took a little plot, ability versus time. Okay? What would you hope to happen? What happens to our ability as we spend more time? Okay, it increases. We see a nice line. Okay? Officially, how much time should we spend for our ability to be awesome? 10,000 hours. That's to become a master in a subject. Do we expect you to turn into a master? I don't think there's 10,000 hours actually in a semester. So we don't expect you to master it, but we do expect you to have some upper understanding level of it. Okay? So it's going to take time to go through and appreciate. For organic chemistry, our line probably looks more like this. Okay? We have to spend more time to get decent ability. Okay? So that becomes kind of a pain. For spectroscopy, it unfortunately looks like this. Okay? Meaning you will spend tons of time and your ability will go absolutely nowhere. Okay? Yes, that is infuriating and frustrating. However, as you continue to spend that time, you will hit a point where all of a sudden your knowledge will drastically improve. Okay? That line for that maximal jump up is what I typically reference at 50 hours. You spend 50 hours, it will be brutal, awful 50 hours. Okay? But you hit that 50 hours, your knowledge on spectroscopy will go through the roof. Pretty much anything I ask you will be easy. At this stage, anything I ask you will be stupidly hard. At 40 hours, anything I ask you will be stupidly hard. Hit that 50-hour mark. Okay? I will do the best that I can to help you work with that and set you up. That's what the videos are for. That's what the practice is going to be for. Kind of make sense? Okay. So one depressing topic to another. Okay. One more address before we kind of get, or almost addressing. You will notice that this file is posted on Canvas as well. I call it spec.org. It's how you should organize your thought process for solving. Okay. You all took 152. In 152 you had ice charts, right? Did you need to use an ice chart? No. Ice charts are completely unnecessary to solving any question in general chemistry. Why do we use them? It organizes your thought process so that you can get to your answer more smoothly and efficiently. That's what this does. Okay? How many instructors in the world use this? One. Okay? Which means if you go to get help from somebody that hasn't been taught by me, there aren't a whole lot that have been. They won't understand what's going on with this. Oh, well, that's too much work. That's because they've already done this. They've internalized this figure. You aren't there yet. Write it all down. Okay? That's what this is for. So, because you watched the video, and I delayed talking long enough that you didn't see what I just erased, there's an IR. What do you see? Time's up. You should have had it entirely solved by this point. 10 seconds. That's how quick IR needs to be. CH, not accurate enough. It is CHSP3. How do you know that?
Multiple peaks that are skinny.
Multiple peaks, I'll accept that. What else? There's a big one. Those signals show up just under 3,000. Okay, so they match the patterning that we would expect for CH bonds, okay, that have an sp3 hybridized carbon, and they show up just under 3,000. Because I can say that those same peak patternings also show up somewhere down in this range, right? Okay, those don't count as CH stretches. Okay, so you need to be able to recognize the range and what they look like. I would argue you've missed at least one more important peak. You have an OH. These ones get a little bit trickier. We'll probably argue that we're looking at carbon-carbon double bonds. Okay. Maybe a carbonyl. All of that information should get written in 10 seconds. That's how quick that needs to be. Notice, did I touch anything in this range?
No.
Okay. That's the fingerprint. Okay. Fingerprint we don't want to look at. Okay, yes, you can identify me by my fingerprint, but nobody has yet come up to know. Any time I've ever interacted with people, asked for my fingerprint to verify that I'm the instructor for the course. Okay? You can use that. You don't want to, so ignore it. Sort of. That was strong wording, but we'll deal with that. Mass spec. Again, we'll give you a little bit longer on this one. Process it. What do we got? Mass spec doesn't give you bonds, unfortunately. I don't know if that was actually right or not, but I'll just write it down for the moment. Time's up. Give you 30 seconds on that one. Mass of 93. So it's called mass spec. So what are we looking at? Mass. The mass. Okay. 93. How'd you get the 93? Well, there's 90. 1, 2, 3. Oh, the tall peak is at 93. The peak furthest to the right, the tallest one, that's the molar mass of your compound. So we know the molar mass of our compound is 93. Minimally, you need that. The next little kicker higher that you should know that is odd, which means nitrogen is present. Okay. We could also go through and put in the negatives. Okay. Is there an M plus 2? So the M was 93. Do we have a peak at M plus 2? No. So at 95, do we see anything? No. So what does that mean? Do we have bromine? No. Do we have chlorine? No. Do we have iodine? What is the mass of iodine? 127. 127. If the mass of my compound is 93, is iodine present? No. No. That's what I expect you to get out of mass spec. We have 1, 2, 3, 4, 5 pieces of information. That's pretty much the bare bones of it. We want to go to the next highest level up in understanding. We can get a possible formula from this. Okay. In that 93, we know we have nitrogen because it's odd. What is the mass of nitrogen? 14. So 93 minus 14, 79. You could help me. Okay, 79. Okay. What is going to be in the rest of that mass? Carbon and hydrogen. Why do you say carbon and hydrogen? Because it's organic chemistry. Yeah, that simple. Okay. So what can we go through and do? Well, we could say I have 1 nitrogen and I have 79 hydrogens. That's possible, right? That matches the formula. Does that give me a valid compound? No. So what do we do instead? We'll take the 79, divide by 12. That's my attempt at long division. 6.58. I'll accept that. That means we have 6 carbons. Okay, because carbon weighs 12. Okay, what's that 0.58? Okay. Well, 79, what was 12 times 6? 72? Oh, see how fast I got that? 79 minus 72 gets me?
7.
I didn't say it out loud, so it wasn't there. 7 hydrogens. So I now have a formula of C6H7N. That is a potential formula. Is there another potential formula? Remember, I could have had 79 hydrogens. What if it was C5? It'd be H what? Would not be H8. It's not an atom for atom swap because hydrogen weighs differently than carbon. What is the mass of carbon? 12. Which means if I get rid of 1 carbon, I need 12 hydrogens to make it up, and I'd have H19N. I could continue to do that, removing carbons. Would all of those be valid formulas? No. Remember, we said 79 hydrogens didn't work. Why not? Not enough bonds to connect everything. If we have a fully saturated structure, CnH2n plus 2, that means every single bond on my carbon has hydrogen as a possibility. That is the maximum amount of hydrogens I can have for a carbon. What is N in C5H19N? 5, which means the maximum amount of hydrogens I can have? 12. I have 19. Is that formula correct? No. What does that mean? The formula for my compound is C6H7N. Okay. How useful are formulas? In my opinion, I think they suck and completely useless, which is why I don't spend the time to figure out the formula. Okay. We have that information. We can do it. I expect you to do that in the homework. I don't expect you to do it on the exam. Make sense? Carbon NMR. This is, since I'm talking a little bit and you're still looking at it, I'll give you 15 seconds. You all watch the videos, right? There's our 15 seconds. Carbon, alkane. Carbon, alkene, or aromatic. And 1, 2, 3, 4, 5, 6, 7 carbons. That's it. That's all I expect you to get. So by knowing where the signal shows up, that gives us information about that type of carbon. The one showing up about 20, that only happens for carbons that are all singly bonded. There's an alkane. The ones that show up between 120 and 160 are all typically due to carbons that are doubly bonded. Okay, not guaranteed, but pretty darn close. Alkenes and aromatics. There are 7 peaks, which means 7 carbons. Does that mean exactly 7? No, it means 7 unique carbons. Because if they aren't unique, where does the signal show up? The exact same place. And we can't differentiate it. Okay? I think I wrote that in less than 15 seconds. Okay? And now we hit HNMR. That one takes a little bit longer. Okay? But we've got some context. I'll give you a minute. See what you can come up with. You may not have watched the video, but I gave you context already on the carbon NMR. This is HNMR, so we've got a little bit more information. Everybody guarantees you'll be able to tell me at least one bit of information off of this. $30 seconds left. $15. Ask your neighbor. What do they say?
Is that right?
But there is hydrogen? No, it's not all you have to put. First thing everybody should have said, there is hydrogen. You have peaks. Use the information that you have access to. There are signals, which means there is hydrogen. If you're on a multiple choice test and one of your answers doesn't have hydrogen, guess what? It's wrong. You can eliminate answers. You don't have to know everything. Right? How many hydrogens are there? 1, 2, 3, 4. What? There's so many more peaks here than there were in the last one. Yes, because hydrogen NMR has an added caveat. Hydrogens that see each other cause their signals to split. Okay? And we get multiple peaks for one signal. There are only 4 unique hydrogens. Okay? We could process some information about where those signals showed up. The ones showing up under 2 are all typically alkanes. That one at 2.5 is a hair above 2. Is it an alkane? I don't know. Okay? That, if you watch the video, falls in the range that I call everything else, which means I don't analyze what that hydrogen potentially belongs to. It is a hydrogen bound to a question mark, because I don't know what it is. Okay? The other ones, because they're alkanes, those are hydrogens bound to carbon. Okay? So I can look at the number of signals. Okay? I can look at the location of the signal. Okay? And here's where carbon NMR differentiates from hydrogen NMR. This signal over here, what can you tell me in comparison to the other signals? It's really big. What does that mean if it's really big? Whatever's making that signal shows up a lot. As in, there's more hydrogen. Okay? I can look at the intensity. And I'm going to have to put that in quotes. Intensity of my signals. And then I can also look at the peaks within a signal. So we get 1, 2, 3, 4 pieces of information that we can pull from an individual HNMR spectra. Right? With all of this bits of data that we've now concluded from the spectroscopy, what we would do is then take each of those pieces, bring them all together into one big melting pot and say, how does this allow me to put together and solve for the overall structure? Right? Yes, you'll notice I did not solve this one all the way out, and I'm not going to, at least this class period. Okay? What you need to be thinking about is testing yourself, looking at spectra, trying to process it, figure what information you can get out of it quickly. Okay? The quicker you can get access to that material, the more likely you'll be able to solve it and put the whole thing together. Spectroscopy as a whole. Okay? Anybody like making puzzles? Or doing puzzles? Yeah, those people that like doing puzzles. Guess what spectroscopy is? It's a little bit worse than a puzzle. Okay? You are taking a puzzle to build the puzzle pieces to then put together the puzzle. Okay? So it's a puzzle within a puzzle, potentially even within a puzzle. Okay? It's inception. Okay? Accept that, use that information and build. Don't start looking at it and saying, well, I don't see the structure. You won't see the structure. Okay? Which is the next frustrating part. You go to a tutor and show them the spectra, they go, oh, well, this is the answer, and they draw out the structure. How did they do that? Remember that sheet that I had with you filling all the information on it? Guess what they did? They did that in their head. Right? They've done it enough that they can do that. Right? Remember that line. As soon as you get it all. Right? But you have to get there. Spend the time, work your way through it. Right? And worst case, it's only 2 hours of video. I think it's closer to 3, but 2 hours of video to go through and look at how to go through and solve. Okay? So, wait a second. That's not supposed to happen. Well, we're going to talk about spectroscopy today. I thought we were going to talk about chapter 5. Apparently I misplaced those slides. So, when we're looking at chapter 15 and 16, okay, what we're trying to figure out is our structure and how we would prove it's our structure. So chapters 1 through 5 were all about, let's draw out a structure. We have these molecules, we have these pieces, let's build things. Right? When we move into chapters 15 and 16, it's how do we prove that that is actually what we made? It's all well and dandy to draw something out, but if you can't prove that that was actually it, you're lost. Okay? Spectroscopy is that proof. Okay? We have several forms of, and they give us different bits of information. The first one is UV spectroscopy, and you might be like, oh my gosh, another one that we have to learn. UV spectroscopy is probably the easiest of these. Okay? It's also one that is technically review. You've already discussed UV spectroscopy in Gen Chem. Okay? Except it was typically associated not just as UV, but it was UV visible light. Okay? And when you looked at it in Gen Chem, it was the same process. It's looking at the electronic transitions. We fire ultraviolet or visible light at a molecule. It excites electrons. Those electrons had to get excited by that energy. We can notice that that light was, or that energy was absorbed, and that gives us information about where the electrons jumped from. Okay? So that is ultimately going to tie back to everybody's favorite subject. Where do our electrons jump from? Orbitals. But when we're in molecules, they're no longer atomic orbitals, they are molecular orbitals. Remember that whole molecular orbital section? Yeah. This is where that comes back, okay, as one version of it, in a simple format, so don't panic. Okay? A lot. IR spectroscopy. Okay? We're changing the energy of the light aimed at our molecule. In UV-Vis, we're using ultraviolet light, okay, and visible light, both of which are higher in energy than infrared. So when we fire infrared at our sample, what happens? UV and visible were low enough energy that they could move an electron. Well, how big is an electron? It has almost no mass. Okay? So if we move to a lower energy, what can we move? Can't move electrons because that was UV. So what are we left with? We just cause the molecule to quake. That's about it. Okay? We scare the molecule and it goes, oh! But it goes, oh! In consistent patterns. Those consistent patterns we can detect and reference in IR spectroscopy. That's what the signals that we were looking at when we looked at our IR. Okay? Mass spectroscopy is a much smaller portion of this class, but what's happening in mass spec is we take our molecule, okay? We looked at high energy, we looked at low energy, and we said, you know what, let's just go crazy. Let's actually use a massive amount of energy. we're going to use so much energy that what happens to the molecule? It blows up. Okay? It may not be the most nice way to describe this, but at least everybody has a rough idea of what's happening with this. If we had a car and we put a bomb into that car and the car blows up, okay, there are people whose job is to do what? Take all of the pieces and reverse engineer where the bomb was placed. If we can do that with cars, guess what we get to do with molecules? The same thing. Okay? So we have the ability to evaluate the pieces that come out and reverse engineer our structure. Fascinating subject. All we're going to narrow it down to is those 5 big things. We throw so much energy at it that, well, it didn't really blow up. There's the mass. Okay? The mass of our ion. Okay? What are the other things we pick out of it? Ultimately coming back to mass. Bromine has 2 isotopes, chlorine has 2 isotopes, iodine is massive. Okay, so they're looking at characteristics of some elements that we typically find in organic chemistry. Okay? The last one is probably the most dangerous or difficult one for students to process, is our NMR, nuclear magnetic resonance. Okay? That is the one that's going to give everybody the most trouble. That is the one that we'll try and spend the most time on in solving and working through. Okay? What's happening there is multiple things. We take our sample, whatever we're studying, we put it in a magnet. Okay, what happens when you put something into a magnet? Attraction. It aligns with the magnet. Okay? Then what do we end up doing with NMR? We turn on a radio. We blast it really loudly at our sample. And the sample goes, whoa! And we can measure the time it takes to go, whoa, back to aligning with the magnet. Yeah. That timing is due to the environment of our atoms. Okay? And we can tie that again back to structure. Okay? Fascinating that we can pull that off. Okay? So, that's our goal with all of these, is just determining structure. So, our electromagnetic spectrum, we got energy, wavelength, all that fun stuff. Questions about that? If you're familiar with the electromagnetic spectrum? No? Yes? Okay. We can look at molecular effects. If we go up to X-rays, we can ionize, meaning what do we do to our electron? What does it mean to ionize something? Take away an electron. So if we use something up in the X-ray range, we're ejecting an electron from a molecule. Right? That's effectively what mass spec is doing. It's ionizing our molecule. The electronic transitions all occur in the near UV and visible light. Okay? So what we're doing is causing electrons to jump different orbitals. Molecular vibrations happens to be in the IR. That's just how it moves, okay? How it oscillates. Okay? We don't break anything. We don't destroy anything. It just kind of sits there and wiggles. Okay? Rotational motions and nuclear spin transitions are what are being manipulated when we look at NMR. Okay? So it's not so much that you need to quantify these, just have a general concept of what your electromagnetic spectrum is, and we are then using different pieces of it for our different forms of spectroscopy. Okay, so let's take a look at ultraviolet and visible spectroscopy. Okay, these are again all our electronic transitions. What we've got here is now an example of a UV-vis spectra. Super exciting. What do we have? What do you see in that spectra? One peak. Where's that one peak? 224 nanometers. Okay? Which is where? UV or visible? It's UV. It's actually pretty deepish UV. Where's your visible range? 800. 800, yes, is red. And 400 is our purple. Okay? So when we look at this molecule, it does not have any absorptions in the visible spectrum. What would that mean about its color? It's not visible, so it's invisible? Clear. Okay? It's going to be colorless. You're right, not visible is right. Okay, just word choice. Okay, so we're looking at a clear sample. Okay, it doesn't absorb any visible light, but it does absorb something in the deeper UV range. Okay, what we're looking at there is the absorption. We could tie that back to transmission and all that fun stuff. We could use Beer's law. Okay, we've got Beer's law written down there. You're all familiar with Beer's law from Gen Chem? No? Okay. A stands for? Absorbance. That was the easy one. What is that symbol? Epsilon. Epsilon stands for? We hardly did it. Oh, that's fun. The extinction coefficient? It is a constant for an individual molecule. Okay? It is how that molecule responds to light at a particular wavelength. Okay? That's what it's describing. It's a characteristic of that molecule. What is B? Really? Who are your Gen Chem instructors? Go yell at them. I won't do that. No, don't tell me. I don't want to know. Is our path length. Okay? If we take a sample, what we're looking at is how light is absorbed. What does it mean if I change the path length? If I have a really wide path length or a very long system where my sample is, what's going to happen to the absorbance? Okay? This should actually tell us, if I have a very large path length, what happens to the absorbance? If B gets really, really big, A has to get really, really, really big. Make B 1, what do we get for A? Ignore those. It becomes 1. Make B 1,000, what happens to A? That's 1,000. Okay, so they are directly related. Does that make sense? We're saying the more substance that our sample has to pass through, the more concentrate or the more light is absorbed. The more time we give our light to interact with our molecule, the more light is absorbed. Yeah, that makes sense. It's effectively a concentration. If you take a thin box, filled it with color, and looked at it from one end versus the side, it looks like the color changed. Did anything about the sample change? No, but the amount of light that had to interact with the molecule changed to go through that distance. The last one, C. Gen Chem. Covalent begins with C, yes, but no. It's a good guess. We're going to run out of space. There's some more dots. Concentration. The more of our individual molecules present, the more light is absorbed. Okay. If we color in very lightly, say in this box, what color is inside that red box? Okay. But most of it is white. So what's the blend of red and white? Pink. What happens as I make it more and more dots? It becomes darker pink until eventually it becomes fully red. So concentration has an effect on absorbance as well. Okay? So what we would do is run a spectrum where we fire light of an individual wavelength at our sample and we see what happens. Did it get absorbed? No? Okay, well it doesn't absorb light then. Okay? And we can generate these spectra. Does that tell us anything about the structure of the compound? In this case, not really. Okay? So what structural information do we get out of it? What's happening, number one. Okay, remember we said we were exciting electrons. For this molecule, if we looked at our molecular orbitals, okay, what would our two highest energy occupied molecular orbitals be? So we said occupied. So if we take a look at this, what are the bonds in that molecule? Several of you have had me ask this question of you, so you should know the answer. What are the bonds in that molecule? Sigma and pi. Okay. How many pi are there? Because? Two double bonds. Okay. Which is higher in energy, sigma or pi? Pi is higher in energy. There's no overlap of the orbitals. Right? It's an indirect overlap. That necessarily makes it higher. What you might be starting to get confused with is not the bonding orbital, but the anti-bonding orbital. Okay? Why are we concerned primarily about the pi? Well, what we're looking at is where our electrons exist. The electrons are going to exist in pi-type bonds. Okay? Those pi-type bonds will be our highest energy occupied orbitals. We won't have any in the unoccupied system because the unoccupied end up becoming anti-bonding. Does this molecule exist? Yes. Should we have any electrons in the anti-bonding? No. Okay? So when we populate, we'll fill up our molecular orbital and we'll have our electrons in those orbitals. What happens when we hit it with UV light? It can excite the electrons. It'll excite the electrons where? It will likely excite the electrons in the pi-type orbitals, the highest energy ones. Okay? Why would it excite the highest energy orbitals? The lowest energy ones are going to require too much energy to get them to jump. Where are we jumping to? Where do electrons exist? In orbitals. Okay. Where can our electrons jump to? So if I take this electron down here, it can jump to that orbital? Why not? It's filled. Where do our electrons jump? Say that again? Unoccupied, or is what Muhammad was suggesting, which might be an easier word, empty orbitals. Okay? To take an electron from that bottom and drop it up to here, we're looking at a fairly large energy gap. What if we took the electron from here and put it to here? Is that an easier energy jump? Yeah. Is that energy jump going to match with our UV? Probably. Okay? So we're looking at exciting electrons from our occupied states to our unoccupied states. Depending on the energy differences between those orbitals, we end up seeing those individual signals. So we can say because it absorbs at 224 nanometers that I have an energy difference between some of those orbitals equal to that wavelength. Do I know which one specifically? No. Okay, but all we're saying is our electrons are jumping. That's all you really need out of that. So what does this do for our structure? Okay. Well, let's take a closer look at our molecular orbital diagram. We said we had 2 pi, right? Okay. 2 pi interactions, which means how many molecular orbitals should I get? It's tricky. We determine our molecular orbitals from the atomic orbitals. To make those 2 pi bonds, how many atomic orbitals did I need? I need 1 p orbital and 1 p orbital there to make that pi bond, right?
Yeah.
How many atomic orbitals was that? 2. Do I have a different pi bond? Yes. Those 2 pi bonds need to come from 4 atomic orbitals, which then means I have 4 molecular orbitals, 2 of which will be bonding and 2 will be anti-bonding. What orbitals are we looking at overlapping? What type of bond? Pi. So we're looking at sigma orbitals? No. What orbitals are we looking at overlapping? Pi orbitals or p orbitals because we're referencing the pi bond. Remember, p and pi, those are ties. We have 4 atomic orbitals. The atomic orbital, 1, 2, 3, 4. It was an appropriate laugh. What happens when those overlap? As we set that up. Remember what we said about our p orbitals? What do we have? Are they the same phase? No. I have a positive and a minus. Okay? Can the electron make that jump? Yes, if same phase. Can it make the next jump? If it's the same phase. What happens if they're all the same phase? They can all jump. Would I expect that to be high energy or low energy? Why is that low energy? I won't accept bond. It's not wrong necessarily.
There's more space.
There's more space. I've provided the electron now not 1 location to exist, but 4 locations. I've given it more space. Okay? When you go to find an apartment to rent or a house to live in, do you find the absolute smallest one? Just that little closet space? Just enough room so you can stand up and you can lean against the wall to sleep? Okay. You're probably going for something a little bit larger. The more space we have, the lower energy, the happier we become. So this is now a very low energy state. Okay? Did they all have to overlap? No. What else could have happened? Well, we reverse them. How many nodes? Okay. 2. Tell me where your 2 are. If you want to know, you're right. There are 2 nodes. Here? What is a node? A place where an electron can't be. Can electrons make that jump? Can they exist in that space? Is there a node there? No. How about through the middle? There we go. There's a node. The electron can't exist there because it can't make that jump. They aren't in phase. Where else is there a node? Horizontal within our p orbitals. Okay. If we compared that to our lowest energy, how many nodes are in that one? 1 right through the middle. When we went up in energy, what did we increase? The number of nodes. Take a second. See if you can't draw 2 more molecular orbitals. So, if we take a look at the drawings that I've got set up, we have 2 different molecular orbitals here. Okay, the bottom one we showed with individual phases, plus and minus within them. Okay? The one above that, I implied the phase difference by shading. You'll typically see that as drawn as shading, not the positives, negatives. Okay, so if we went through and drew this out, that would be our bottom one. So there are 2 more possibilities. So we can draw out our p orbitals here. And now it's going to come down to how we appropriately shade those. Okay, before we get too excited and start coloring these things in, as we move from our lowest energy to the next highest up, what did we do? We increase the nodes by 1. What's going to happen when we move up to the next one? Increase nodes by 1 more. To the next one? Increase nodes by 1 more. Okay? So in theory, you have some drawings set up. And because he's not here, let's go ahead and just take advantage of his stuff. Dude, you didn't draw it.
It was negative, positive, positive. Like this.
So, what do we got?
So this would be the 3rd node, because this one was the 4th. So it was positive, negative.
So if I'm going to draw it out exactly as shown, I'm going to do it this way anyway. Sorry, deal with it.
Well, it's 4.
If we take a look at that, is that a possible organization? Yes. Should that be the next highest from the ones drawn? Why not? There are 4 nodes, and we started with 2. So that can't possibly be the correct organization. Okay. Oh man, I'm going to go back too far. So, oh, catch up, drawing, thank you. So I agree with that as a possibility, but that had 4 nodes, so that's likely going to be our highest energy. Okay. And then we had another possible drawing. Yes, but I'm going to switch it up on you. A couple people drew this.
Oh, because there's only 2 nodes on there.
Interesting. There's only 2 nodes, though. To go up in energy, what do I need? 3 nodes. So that one does not officially go up in energy. That is an example of a degenerate orbital of the second one. Okay? We typically don't reference it because it is not symmetrical. When we're drawing out our orbitals, we need to make sure they are symmetrical. Okay? So the last example that we could get will be this one. If we count our nodes, 1, 2, 3 nodes. Remember how we talked about bonding and anti-bonding? You're like, oh God, that was awful. We just said that we labeled it out. Okay, well let's come up with an explanation on where those bonding and anti-bonding are coming from. Take a look at this, the lowest energy one. What kind of interaction is happening here? Favorable or disfavorable? Favorable. And the next one. Favorable. And the last one? Favorable. So we have 3 favorable interactions. Okay? Saying the electron can jump. So what is the average result there? You average 3 favorable divided by 3, we get favorable. Which would suggest bonding. Take a look at the highest energy one. What's that interaction? Non-favorable, I'll accept that. Next one. Non-favorable, next one. Non-favorable. What's our average result? Non-favorable, so that's suggesting it is anti-bonding. Number 2. What do we have there? Favorable, here. Non-favorable, next one. What's our average? 2 of those are favorable, 1 is non-favorable. Our average is favorable bonding. Here. Next one. Next one. Average. When we're referencing these as anti-bonding, we're not saying it's not a bond, okay, and it doesn't exist. These exist. Okay? We're just saying it's a non-favorable interaction. That interaction is still possible, it's just not a good one. That's it. Okay? I now have my molecular orbital diagram for this molecule, okay, or the highest energy molecular orbitals. Okay? How do I know they're the highest energy ones? How did we start this whole process off? Pi bonds versus our sigma bonds. The pi bonds were higher in energy. Those are going to be the ones most likely to react with anything. Those are going to be the ones we're most concerned about. Okay? If we now want to simplify this a little bit, clean it up, we can turn it into 1, 2, 3, 4 molecular orbitals. Okay? How many electrons go into those orbitals? How many electrons went into the red pi bond? 2. How many electrons went into the purple pi bond? How many electrons need to go into my pi molecular orbitals? 4. First 2, lowest energy. Next 2, next lowest energy. Do I place any more electrons? No, because I'm out of electrons. Okay? What happens if I then use UV light? I can take that electron and excite it to a higher energy, which means what happened to the pi bond? It broke. What can happen with a pi bond when it's no longer a pi bond? Rotate, and we can transition between, say, a trans isomer and a cis isomer. That sounds familiar. Yes, it does, yeah. Okay. We want to come through and label these. We can call them all molecular orbitals. Okay. I can call them molecular orbital 1, 2, 3, and 4. I want to be a little bit more creative. Of my bonding ones, which of those electrons is most likely to react? Okay. The blue bonding or the red bonding? Blue. Why? Higher in energy. I want to refer to those electrons. Okay. I need to be able to name that orbital. Okay, well, it's a molecular orbital, so I could call it Mo. What's the problem with that? They're all molecular orbitals, so I need more information than that. Okay. What else do I know about that molecular orbital? Yeah, it's bonding. What's different from it in comparison to the ones above it? It's easier than that. So much easier than that. Erase all of that. That's not there. Stop looking at those words. Describe to me the difference between line number 2 and line number 3. It has electrons. Okay? So that Mo is an occupied Mo. So I have OMO. What's the issue with calling that one just OMO? Number 1 is also an OMO. So what is different about molecular orbital 2 and molecular orbital 1? It's higher in energy. I can call this HOMO. Highest occupied molecular orbital. Where would I expect that electron to jump to most easily? The very next energy level up. Okay, the very next one. So I want to reference that one. Okay, that is also a Mo. Continue to describe it. It has no electrons. With electrons was occupied, no electrons will be unoccupied. So we have UMO. But the highest energy one is also an UMO. LUMO, our lowest energy, unoccupied molecular orbital. When we're talking about electronic transitions, the electronic transitions are typically happening between the HOMO and the LUMO orbitals. So when we're looking at UV light, that is our highest energy or our biggest intensity signal. What happens if we change the structure of our molecule? Let's see, the next slide, give it to me. So there it looks pretty, right? Ta-da, pretty. That doesn't look as pretty. What happens if we change our structure? I have more electrons. I have more molecular orbitals. Okay? But I have a finite intensity or a finite height of the energy of my orbitals, which means I'm occupying those orbitals in the same space, but I have more orbitals. What happens to the distance between the HOMO and the LUMO? It gets smaller, which then means the amount of energy needed to excite the electron between the HOMO and the LUMO goes down. If we look at our individual molecules, ethene requires 161 wavelength energy, light, to cause it to be excited. If we jump to buta-1,3-diene, the wavelength jumps to 217. Oh, but the number went bigger. What's the relationship between energy and wavelength? Inverse. Meaning, as we increase conjugation, more double bonds, what happens? We see our wavelength get larger, the energy to excite those electrons gets smaller. And we start shifting out of the UV and into the visible light spectrum. When you think about color, those colored compounds are due to organic molecules and double bonds.